In this paper, we talk about a flexible connector for soft modular robots based on micropatterned intersurface jamming. First, we will talk about the background and our research motivation. Soft modular robots have many unique advantages. For example, more adaptation to the environment and safer interaction with the human beings. Modular robots, on the other hand, compared to conventional fixed morphology robots, have the potential to be more functionally flexible and robust. If combined together, a soft modular robot enables even more flexibility and safer interaction with the changing environment than traditional robots. However, it has remained challenging to create deformable connectors that can be integrated into soft machines. So in this work, we aim to design a flexible connector that can be integrated into soft body modules without increasing the system's overall stiffness. And here we start with some previous works. Most state-of-art modular robots propose rigid building blocks with incompliant connection mechanisms, such as magnets and mechanical latching. But despite the fact that rigid connectors provide stability and controllability to the robotic systems, it limits the overall flexibility. And one possible solution to create flexible connectors is to integrate electroadhesion pads into soft modules. However, electroadhesion can only support a lightweight and needs continuous external power supply. Our approach is to use micropatterned dry adhesives to connect the modules. These dry adhesives are essentially soft elastomer pads with microfeatures on one side. While pressing two patterned surfaces against each other and drag them in the desirable direction, repeatable and robust micro-zip fastening effect can be achieved. These adhesives need little initial pressure to engage and maintain strong bonds without extra pressuring afterwards. Following these concepts, we created a single layer of anisotropic micropatterned adhesives with silicone elastomers as shown in the picture. Initially, the jamming effect is off since there is zero contact. When two pieces of adhesives are engaged with each other in the opposite direction, the microstructures enter each other's cavities to form interlocking, and jamming starts. The intersurface jamming force is expected to be the strongest in the opposed shear direction, where the most contact area is presented. Therefore, the jamming effect between micropatterned dry adhesives can be directional, thus prevents them from attaching accidentally. The micropatterned dry adhesives are fabricated by casting silicone elastomers onto a micromachined surface mold. The metal mold is machined by ultra-precision diamond ruling that produces an optical level surface finish. Generally, a single connector can be decomposed into three components as shown in the figure. The main body actuator, which is essentially a soft pneumatic gripper with inflatable chambers. The pneumatically actuated main body can engage and disengage the dry adhesives on two connectors and adjust the connection force through chamber inflation pressure. Another component is the two origami-inspired dampers on both fingertips. These dampers are not connected to a pneumatic power source and serve only as passive alignment mechanisms to maximize the contact area of the dry adhesives. The last component is the compliant connector tail for connection to another connector unit. The compliant tail is ladder-shaped, thus it can deform to change orientation when subjected to external disturbance force or environmental constraints. Next, to characterize the performance of the flexible connectors, two experiments were performed on a custom-built platform. The first experiment aims to evaluate the connection force between two connectors under different chamber inflation pressure and under different planary rotational angles. A total of 6 inflation pressure and 3 planar angles were tested from 0 to 2.8 bar and from 0 to 30 degrees, with each case repeated for 5 times. 4 adhesive pads were used throughout the entire experiment, which gives a constant contact area of 4.5 cm squared. From our measurements, a maximum connection force of 23.52 Newton was recorded at an inflation pressure of 2.8 bar. As expected, the maximum connection force increased with the inflation pressure. But surprisingly, an average maximum connection force of 1.75 Newton was recorded at zero inflation pressure. This result indicates that intersurface jamming between dry adhesives is effective as long as contact occurs, even with minimum preload pressure in the normal direction. We argue that this characteristic is especially beneficial when high pressure is unavailable, for example, in the case where an ultra-soft main body is presented. We found also that through a planar rotation of 30 degrees, as shown in the figure, resulted in a drop of maximum connection force from 17 Newton to 9.7 Newton. The remaining connection force, however, is still large enough to maintain a robust connection. The drop connection force is mainly due to the loss of contact area and the peel-off effect caused by the stretched singularities. To expand our understanding into a three-dimensional way, we measure the connection force when the actuator is rotated along the y-axis, as shown in the figure. A total of 3 different angles were tested from 30 to 90 degrees at different inflation pressure from 0 to 2 bar. In the measurement results, we found around 50% loss in connection force for all 3 angles at high inflation pressure compared to the shear direction we measured before. At last, to further illustrate the advantage of jamming-based connectors, we replaced the micropatterned dry adhesives with smooth silicone pads and pure TPE respectively. Then, we measured the shear force like before. The results are illustrated in this figure, where we can see that the jamming-based connector has a more than 50% increase in connection force than the ones with silicone pads, and is almost 10 times stronger than the pure TPE connectors. To conclude, our work presents a first study in design, fabricating, and characterizing a flexible connector for soft modular robots based on micropatterned surface jamming. The connector we propose can support a maximum linear load of 23.52 Newton and a 10.86 Newton load under 30 degrees of planar rotation. The connector also shows selective attachment properties. The immediate pursuit of the future study is to improve the performance of the jamming-based connectors under very low inflation pressure. We will also further implement the connectors to build entirely soft modular robots.